Okay, so this weekend we will have the first midterm. So any questions? I mean, we can use this week also to review the previous chapters. Of course, if you have questions. If you don't have questions, I will just continue with the new chapter. Okay, so the question is, how do you distinguish Q enclosed and Q total? Do you have an example of a particular question? Well, let's see. Let's just have a bunch of charges, plus Q1, Q2, Q3, Q4, Q5, and Q6. Okay, let's imagine this surface. Surface 1. What is Q enclosed for surface 1?
0.
It is 0. Let's imagine such a surface. Q enclosed for surface 2. Q4 plus Q6. This is surface 3, Q enclosed for surface 3. This is my surface, Gaussian surface. This is the sum of all of it. Q1 plus Q2 plus Q3 plus Q6.
Geçen yılın sorusu, iki tane plate var. D/2 uzaklıkta A var, D/2 uzaklıkta E noktası var. İçine bir silindir çizerek Gauss surface alıyoruz. Birisi artı, birisi eksi.
Okay, so this is plus sigma, this is minus sigma. The separation is D. Here you have a point A. This is D over 2. This is point B, C, and some point D over here. This was the question. Well, the figure of the question, let's say. So what is confusing you?
Orada bir silindir aldığımız zaman Gauss surface olarak burada hangisinin Q total veya Q enclosed olduğu ile ilgili biraz kafa karışıklığı yaşadık. Çünkü plate'e aslında dokunuyoruz. Gauss surface aslında plate'ten bir parça alıyor.
Well, let's take such a Gauss surface. This is our Gauss surface with some arbitrary top. What is the Q enclosed? You have, let's say, the area is A. The enclosed area here is A times minus sigma. Plus A times plus sigma from the bottom plate. So the enclosed charge is 0. So there is no charge. The net charge enclosed by this sphere is 0. You can take another surface. Let's say this one. Again, let's say let's call the surface area S. The surface area, let's say, is again S. Q enclosed here is just plus sigma times S. Because sigma is nothing but the charge per unit area. The area of this plane that is inside my cylinder is just S. So the total charge is the area times the charge per area. So that is the total charge plus S, plus sigma times S. Let's solve this problem using Gauss law. Now, if you want to apply the Gauss law, the first thing you have to do is you have to know something about the electric field. Now, what can you say about the electric field? What is its direction and why? I mean, in such a problem, for example, last year's this question, people just took some cylinders like this for the Gauss surface and applied the Gauss law, and they got 0. Because why do you take the cylinder? You have to first explain me why you choose a cylinder as a Gauss surface.
Çünkü sadece side tarafını hesaplayacağımız için.
Why do you only calculate the side?
Çünkü surface'ler şeyi bölerken bottom ve top'ında 0 olduğunu söylemiştik elektrik alanı.
Okay.
Dolayısıyla dışında zaten plus ve negatif sigmaların dış region'larında elektrik alan 0 olacağı için silindirin side'ı hesaplamak daha kolaylaştırmıyor.
You see, this is an example, sorry. This is an example where a significant number of students had similar answers, or they took the cylinder and considered the sides. Well, this is a typical example of what happens when you memorize things without really understanding them. We did calculate the side, but that side was for an infinite wire. Only for that case we take the sides. In this one, the sides would not contribute because first you have to understand that argue that the electric field is vertical. Since the electric field is vertical, it is perpendicular to the surface vector on the sides. So there's no contribution to the flux. Well, let's take such a cylinder. Was it you last year? No. Now, there were some students who also assumed horizontal spheres, horizontal cylinders. Now, of course, if you take such a horizontal cylinder, in that case, the electric field will be vertically upward. So there will be no contribution from the sides. The only contribution will be from the sides. But you see, you have this cylinder. May I take one page? Okay, this is your cylinder. So what is the direction of the electric field? It is always up. So here at the top of the cylinder, the electric field and your surface vector are in the same direction. So that is nice. At this point, the electric field is pointing upward. The surface vector is pointing in this direction. And there's an angle. What is that angle? You have to calculate that angle. So of course, you can solve this problem. This is still manageable. But the integral of the electric field over this surface will not be just the surface area times the magnitude of the electric field. It will not be such simple.
Does it matter if we had a cylinder or something else? But I think the only matter in that situation is that we need a surface which is perpendicular.
You see, the easiest things to integrate over are constants or 0. 0 is quite easy to integrate. It gives 0. So that is how we determine the surfaces. Now, you first have to determine for which surfaces the integrand will be either constant or it will be 0. That is the first thing to do. And in order to determine that, you have to know something about the properties of the electric field. Okay, this is a plane, infinite plane. We have discussed the infinite plane, so we already know that the electric field created by an infinite plane is vertical and uniform, independent of the position, etc. Since that's something that we had already discussed, you have to explain it in the book, in the exam. I mean, you cannot just say that the electric field is sigma over epsilon 0 or sigma over 2 epsilon 0 in the Z. You have to explain why. I mean, that is one of the formulas that I will be giving to you. In the cheat sheet, in the formula sheet, the answer is already there. So that's called a cheat sheet. I mean, it's just I have prepared it instead of you. So the answer is already there. Just writing the answer in just below my question will not gain you any points. Why is it so? Now let's come back to this one. Well, there are various things you can say. My solution in this example that I distributed to the students was just to treat them separately. Now, I said that, okay, if you take one infinite plane, nothing changes if I move from side to side. So the electric field should not depend on whether I'm looking at this point or I'm looking at this point. It shouldn't change. The bottom is exactly the same as the top. So the electric field at the bottom and the electric field at the top should be the same. And if I rotate it, this is my plane. And if I rotate it, just imagine it's infinite. Again, nothing changes. So nothing changes if I'm considering this point over here, or this point over here, or this point over here. Furthermore, the electric field cannot point in this direction, let's say. Or it cannot point in this direction because it will not be symmetric. It will be either changed by translation or by rotation, which shouldn't be. So the only possibility is that the electric field is vertical. That is the only possibility we have. Now, if the electric field is vertical, these are the electric field lines, bottom and top. Well, already just plotting these electric field lines tells you that it has to be uniform. So the electric field lines are, there is no place in this graph where the electric field lines are denser than the other ones, the other places. And the density just tells me directly what the magnitude is. Since the density of the electric field lines everywhere is the same, so the electric field vector should be the same everywhere. So that already tells me a lot about the electric field. I didn't use the Gauss law yet. I know that it is vertical. I know that it is uniform. Of course, it is pointing in different directions in the top and in the bottom. Now let's go back to this one. We already know the electric field for 1, infinite plane. Well, we don't know it exactly. We know its magnitude is uniform. We know that it is vertical. So we can just look at these two cases. For positive and negative, well, the electric field will be pointing just in opposite directions. I have the same density for this one and for this one. They're just plus charges are replaced by minus charges. And in this region, I know that the electric field of this one should be pointing away. The electric field of this one is pointing towards the charge, so they will cancel over here. So I know that the electric field is 0. Similarly, the electric field will be 0 over there, and I know that the electric field in this region is uniform and pointing upward. So these are things that I have to determine before using the Gauss law. I know already a lot about the electric field. Now I should choose a Gauss law to determine the magnitude of the electric field. I still don't know the magnitude. Well, the electric field lines are vertical, so if the area vector is horizontal, there won't be any contribution. Well, the area vectors are horizontal only if my surface is kind of a wall, a vertical going from top to bottom. So I can use such segments, such areas. Because the electric field vector is in this direction, area vector is in this direction, they are perpendicular, so there won't be any contribution from such surface patches. I can take a horizontal area, because in this case the area vector and the electric field vector will be pointing in the same direction, there won't be any changing angles. So I can just, their scalar product will just be a constant, the electric field, the vertical component of the electric field. So that's also a constant. So great. So I already know two pieces of surfaces that I can use to construct a closed surface. So I can just imagine, let's say, such a closed surface. Well, the area at the top or at the bottom, it need not be a disk. I mean, it can have an arbitrary shape. The only thing that is important for me is that the top and the bottom areas should be horizontal, and the side areas should be vertical. Those are the only things I need. And in such a case, the side wouldn't contribute. Now, the problem on choosing such an area is that the electric field vector and the surface area vector, they make changing angles. The angle between them is changing. You can still do it, you can still deal with it, but it will be more work. And if you don't assume a perfect cylindrical sphere, perfect cylinder with a spherical area or some particular form of area, I mean, you cannot even calculate it exactly. But for a cylinder with an area over here that is a circle, that's a disk, then you can calculate that one, but it will be a lot of work. Now let's stick with this one. I already know the electric field is non-zero only here. They are zero over here. They are vertical to the top, to the bottom at that point. So I can just go ahead and look at E dot ds over that area, over this one. Now I can split it into two, the top part plus the bottom part plus the side. Well, the contribution of the top from this area over here, it is zero because the electric field is zero over there. This is zero, so the whole integral is zero. On the side, from the sides, why? The ds vector or the area vector is horizontal. At this point it will be pointing in that direction, at this point it will be pointing in this direction, but at every point it will be horizontal, whereas the electric field is vertical. So whichever point I consider on the side, this E dot ds is always zero. It's not the electric field that is zero or the ds that is zero, but their scalar product is always zero. Which is a constant. It's easy to evaluate. The integral is zero. Let's look at this one. What is the angle at the bottom? What is the angle between electric field and ds? We don't know. But we know that E is equal to, at the bottom, some E0 in the z direction. We are trying to determine this E0. So it's in the vertical direction, which I call the z. I call this one the z direction. So electric field it has some component in the z direction. I don't know whether it is positive or whether it is negative. What's its value? I don't know that. Well, from the figure, I can tell you that if this sketch is correct, E0 should be negative, but I don't know that. I will just find it out at the end of the calculation. Now, ds, remember this area vector is a vector that is perpendicular to the surface, and it has a magnitude whose magnitude is equal to the area itself, the very small area. It is in the z direction. Now, this ds is the magnitude. It's positive. And then I can determine E dot ds, which is E0 times ds. This is the scalar product, which I should integrate. Well, this is a constant, so it's easy to integrate. I can just take it out of the integral. If I take this out of the integral, what remains is just the sum of these areas of very small patches making the bottom area. And if we assume it is well, let's just, did we give it a name? Yes. The total area is just S. So E dot ds evaluated at the bottom surface is just E0 times S. This is the integral of E dot ds over the whole surface, over the whole closed surface. Because the difference of E dot ds over the closed surface, the difference with this one are terms that are zero. So they are the same. Now we are using the Gauss law, which states that this has to be equal to the enclosed charge divided by epsilon 0. Now let's look at here. What is the charge enclosed in the cylinder? S times minus sigma. S times minus sigma over epsilon 0. So which tells me that E0 is equal to minus sigma over epsilon 0. Why should it be 2s? Well, you see, I splitted my integral already into various pieces. And I'm not usually in the exam I will not be asking you to evaluate complicated integrals, but nevertheless you should know what an integral is. An integral of this form just tells you that you have a closed surface. You have to divide that closed surface into very small patches, and then you have to calculate this thing for each one of the patches and sum them up. This is the meaning. So I first splitted the patches into 3 parts. First, the patches at the top at this area, the patches at the bottom in this area over here, and the patches on the side. Now, when I'm evaluating this integral, when I'm evaluating this integral, I only consider the area at the bottom, not the top. And the area of the bottom of my cylinder is just S. The other one, at the top, it just gives me 0. Well, you see, that problem is a single wire, single plane. You see, that is why it is important to first analyze the problem and know what some properties of your electric field. For example, if I wanted to calculate the electric field of a single plane, charge plane, I would take the cylinder like this, and I would get a non-zero contribution from the top and also a non-zero contribution from the bottom. They will be equal, and so I would have E0s from the top, E0s from the bottom. And that would give me the total integral to be E0 times 2s. Because I have the electric field at the top, and also I have an electric field at the bottom. In this question, I don't have an electric field at the top. So this term does not contribute. So this is why it is important that you first understand your electric field before trying to apply the Gauss law. What about conductors? They are nice. We use them.
Infinite sheetle isolate conductor infinite sheetle non-conducting infinite sheet arasındaki fark.
Well, you see, is the charge uniformly distributed? Then there's no difference. Because you see, what determines the electric field is not the material. What determines the electric field is the distribution of the charges. Do you know the distribution of the charges? If you are given that the charges are distributed in such a way, it doesn't make any difference whether the charges are part of a conductor or an insulator. Because as long as the charge distribution is fixed, you know the electric field. Whether they are part of an insulator or part of a conductor, there's no difference. The thing is, if you don't know a priori the charge distribution beforehand, for example, in a conductor, you can say that you can imagine an insulator, and you put a charge on a given point in the insulator, inside the insulator. Since it's an insulator, the charge will stay there. So that is your charge distribution. Nothing will change. If it is a conductor, if you put a charge inside the conductor, it will distribute itself over the surface. Well, if your conductor is a sphere, it will be homogeneously distributed. So that is how you can determine the charge distribution. But once you determine the charge distribution, the electric field will only depend on what your charge distribution is. So these infinite planes, I didn't specify whether they are conductors or insulators, because I don't care. I know the charge distribution. So once you know the charge distribution, that's it. I mean, you just go ahead and calculate the electric field using the charge distribution. If you don't know the charge distribution, then you have to somehow determine the charge distribution, whether the charges were initially in insulators or in conductors.
In this example, like we are dealing with conductors and insulators, we did it in the class, but we said like in conductors, it's sigma over epsilon naught due to the negative charge can exist due to its exist in one side, and if the other side is cancelled because of the negative charge inside the insulator, inside the conductor. But in insulators, it's all negative or positive, that's why it's sigma over 2 epsilon naught.
I don't remember that.
In some surfaces,
Okay, so let's just imagine we have this surface.
and in the surface of the conductors, the positive charge outside and the negative charge are inside, on this side.
Okay, let's look at this one. Now, let's look at this one. We have a conducting sphere. And then we have another conducting shell. They're both perfect spheres. Everything. Their centers is common. Let's just imagine that initially we put a positive charge, positive Q1, let's say, at this point. And we distribute a charge, let's say, negative Q2 on the outer surface. Now let's say positive Q2. Uniformly on the outer surface. This is initially how we created. I just put one positive charge over here with charge plus Q1 and positive Q2 charge on the outer surface. Then when we reach the statistics, what is the charge distribution, what is the electric field, etc. Now, if these are insulators, well, nothing will change. The charges will stay where I put them because they are not free to move. It's an insulator. So what will happen is, of course, ignoring the effects due to its dielectric properties, we can say that, okay, the total charge the total electric field here will be as if there is a charge Q1 plus Q2 at the center. Total electric charge in this region will be as if there is a charge Q1, no, up to this center, will be as if there is a charge Q1 right at this point, and that's it. Nothing will change. Now, if it is a conductor, what will happen is this charge Q1 will just distribute itself over the surface uniformly. So if it's an insulator, after electrostatistics, after static configuration is reached, the electric field created by this one will be just a point charge over here and a spherical uniformly charged shell over here. That's it. Because we already determined the charge distribution from the initial conditions and the fact that this is an insulator. And once we determine the charge distribution, we calculate the electric field of that charge distribution. Now, if it is a conductor, now, although we distributed it like this initially, what will happen is this plus Q1 will be distributed over the surface. So this will move to the surface, and I will have a plus Q1 charge on the surface. Now, what did change in this region? This wouldn't change anything, but inside the sphere now the electric field is 0. In this case, when it was an insulator, the electric field in this region is non-zero because I have a plus Q charge over there, plus Q1 charge. In this configuration, if it's a conductor, when we reach statics, the electric field inside the conductor will be 0. Now, the second point is, in this region, since it's a conductor, there shouldn't be any electric field. But that means that this plus Q1 charge will attract negative charges in this conductor. And so the inner surface will be charged negatively. And the total charge in this inner conductor, inner surface of the conductor, will be minus Q1, exactly equal to this one. Now, why? Because I can just imagine a Gauss surface that is lying completely in this conductor. But for such a Gauss surface, the electric field is 0 at every point on the conductor, so the integral of the electric field over my Gauss surface would be 0. That tells me that the enclosed charge should be 0. But the enclosed charge will be this charge, there's nothing it will go, it stays here, plus some possible charge on the inner surface. And since it has to be 0, the total charge enclosed, I have to have a total charge of minus Q1 on the inner surface. And so what is the charge on the outer surface? The total shell has a total charge of plus Q2. Minus Q1 is here, so I should have plus Q2 plus Q1 on the outer shell. Now I determine the charge distribution. I can go ahead and calculate the electric field. So it will be just, I have one spherical charge surface here, another one over here, another one over here. And I should just go ahead and calculate the corresponding electric field everywhere. But once you determine the charge distribution, the fact that those charges are part of a conductor or an insulator, it doesn't matter.
That the smallest amount of charge that we can think of was the charge of an electron, which is determined by the main field. But we had more, but we couldn't count them as independent, we couldn't place them in places. We couldn't manipulate them. But what would happen if we just put one electron charge inside one spherical conductor? It was just, because we can't uniformly distribute stuff to the surface.
Well, let's say we have already seen partial polarization, right?
Yeah. So it will be partial.
If you look at the hydrogen, the water molecule, I mean, it's usually plotted as a dipole. These ends should be slightly positively charged. This end should be slightly negatively charged. This slight positive charge is not an integer multiple of the electron or a proton. Well, that is one thing that might happen. But anyway, in this class, we are interested in continuum. So we can still imagine as small charge as possible. There was one more question over here. This one. You see, the total charge of my conductor is Q2. The charge is conserved. I mean, they can just move from point to point, but the total charge has to be Q2. Now, the total charge of this conductor would be, when we reach statics, the charge of the inner surface plus the charge of the outer surface. The sum has to be Q2. We already know that since I have a charge plus Q1 inside in this cavity, the inner surface should have a charge minus Q1. But the sum should be Q2, so the outer surface should have Q2 plus Q1. If we add this one, I get Q2.
Can we use the second plate plus sigma gives us the
This one,
yes,
the second plate.
yes. I mean the electric field is minus sigma, but can we use plus sigma? For example, we select the gas block second plate, not first plate.
No, hold on. Can you repeat it? We have this plate.
Yes.
Okay, let's repeat this problem, but using a cylinder positioned like this. Let's do that. Let's imagine you consider such a plate, such a Gauss surface. Z-axis is again in this direction. E is E0 times Z in the Z direction. And let's just integrate E dot ds. Again, we can just split it into three parts, the top, the bottom, and the side. Now, what is E dot ds at the bottom surface? 0, there's no electric field. What is E dot ds on the side? It is also 0 because in this region at least, E and ds, they are perpendicular to each other. In this region, E is 0 anyway. So this is again 0. This is 0. This is 0. So we only have a contribution from this side. What is E? Well, E is this one. What is ds over there? It's in the minus z direction. This is the magnitude, ds minus ds in the z hat. Now, E dot ds is just minus E0 times ds. So the integral over the top of E dot ds is equal to minus E0 is a constant. The remaining integral is just the sum of the areas of the patches making the top surface, which is S. So minus E0 times S. What is the enclosed charge? Plus sigma times the surface area, and the Gauss law tells me to divide by epsilon 0. So I obtain again E0 is equal to minus sigma over epsilon 0. So the electric field is pointing upward. I still have the minus sign. Now, one thing that you have to pay attention to is that, okay, the electric field in this region is created by both the charges on this plus sigma plate and also on the minus sigma plate. But in the application of the Gauss law, I only have the charges inside my Gauss surface. I don't consider these ones. They are already automatically taken into account.
How can we show that there is no electric field outside of the plates? How then?
Well, the way we did in this problem,
I mean, we just assume that there is.
not really. I mean, we first argued that the electric field is of a single uniform infinite plane is uniform. That was our first argument. We said that the electric field is uniform. It doesn't depend on the position. And then we looked at the R configuration. Let's say this one. At this point, this plus sigma charge will create an electric field pointing downward. Minus sigma charge will create an electric field pointing upward. And they have the same magnitude because we first argued that this infinite plane creates a uniform electric field, so their magnitudes are equal. So one is pointing up, the other one is pointing down, so the sum of the two electric fields in this region is 0.
If that's right, but how we show it with Gauss?
We don't. We don't show it by Gauss law. We first show it by other means, using symmetry arguments. Then, once we already know something about the electric field, like in this one, we already know that the electric field is 0, the electric field is 0, the electric field is uniform over here. Once we know that, then we can use the Gauss law to determine the electric field over here. If you just go over all the examples that we did on using the Gauss law, we first determined some properties of the electric field. For example, when we looked at the electric field created by an infinite wire, we first showed, not by using Gauss law, by other means, that the electric field was uniform and always pointing away from the wire. That is the first step we had to do. In showing that in calculating the electric field of a unit charge by using Gauss law, a point charge, we first showed that the electric field has to be radial, in the radial direction, either away from my charge or towards my charge. And then we determine the magnitude of the electric field. Now, Gauss law doesn't tell me. We cannot use the Gauss law to determine these properties. In fact, let's do one more example before continuing with your questions. With a dielectric, you mean? Hemisphere. Well, let's say a hemisphere. Can we use the Gauss law to determine the electric field of a hemisphere? Okay, my first question, what is the direction of the electric field? What do we know about the electric field created by this hemisphere? We don't know. Why should it be radially out? Hemisphere is this one. Now, first of all, if I rotate it like this, my charge distribution changes, and hence my electric field should also change. So it cannot be radially out.
It's either upwards or downwards. It's either upwards or downwards.
Inside what? Inside what?
The direction of the electric field.
I don't know. What is the direction of the electric field? What can we say about the direction of the electric field? So because that will guide us to choose a suitable Gauss surface. And then we can evaluate the surface integral and obtain the electric field.
Eğer total flux'ın 0 olursa, tamamını alırsak ki sanırım total flux çünkü yukarıdan girip aşağıdan çıkan.
No, you see, this is our charge distribution, right? Did I understand correctly? We have such a charge distribution, let's say uniformly distributed over the surface. What is the electric field? How can we use Gauss law to calculate the electric field? Well, we can't, because we don't know the electric field that this will create doesn't have enough symmetries so that we can just deduce certain general properties of the electric field and evaluate this integral. We cannot evaluate this integral for whatever surface you can imagine without knowing the electric field. I mean, for this problem, you see, Gauss law is valid. Gauss law will still hold if you imagine such a surface, A dot ds will always be equal to the enclosed charge over epsilon 0, whatever charge you put on that shell. But since you cannot say that the electric field has some certain properties that will simplify the evaluation of this integral in terms of some unknown parameters that are left that we couldn't determine, this law is valid but useless. So only in very special cases we can use the Gauss law to determine the electric field. And those are cases which has a huge number of symmetries. Now let's do this example. I have these two spheres, two planes. Let's say this has a charge distribution sigma 1, this has a charge distribution sigma 2. Not necessarily plus sigma and minus sigma. And I don't know the electric fields. I want to determine the electric fields. Now, if this was plus sigma, this was minus sigma, as in the previous example, I could have said that the electric field here and here, it should be 0. But in this one, I don't know. So let's give them just names. Let's assume, let's just choose some direction of the electric field. Here, this is E1. Here, it is E2. Here, this is E3. Now, I will still, since the electric field lines should be uniform, in this region, the electric field is constant. In this region, the electric field is constant. In this region, the electric field is also constant. So I have 3 regions with constant electric fields. And I will be trying to determine the electric fields in each one of those regions. I have 3 unknowns. Okay, E1 is equal to E1 in the z hat, E2. Let's say it's E2 in the z hat. E3 vector is equal to E3 in the z hat. And again, these E1, E2, E3s can be negative or positive. I don't know. It will depend on whether these sigma 1s and sigma 2s are positive, negative, which one is larger in magnitude than the other one. It will depend on many things. So I will allow E1, E2, and E3 to have some arbitrary signs. So I have 3 unknowns. I need 3 equations to determine those 3 unknowns. So I can imagine 3 different Gauss surfaces. Well, let me just write them down. This is one Gauss surface. This is the other Gauss surface. Let's say this will be the third one. And just hope that these 3 Gauss surfaces will give me enough equations to determine the electric fields everywhere. Now let's start with the first one. Now this one I will be doing a bit fast. Let's say this is my S1, this is S2, this is S3. The integral of E dot ds over this one. Again, I only receive contribution from the top and the bottom, not from the sides, because on the sides, the S vector will be perpendicular to the electric field. On the top, the electric field is upward. I will choose the surface vector to be upwards. So they are pointing in the same direction. At the bottom, the electric field is in this direction. The S is pointing in the opposite direction. They are pointing in opposite directions, so there will be a minus sign over there. So this will be E1 minus E2 times S1, which should be sigma 1 over epsilon 0, sigma 1 times S1 over epsilon 0. So this tells me that E1 minus E2 should be equal to sigma 1 over epsilon 0. Well, this is kind of nice, because it tells me what the charge distribution is by just looking at how the electric field changes right at the top and at the bottom. For example, you can just say that this is a conductor, so very close to the surface of the conductor, the electric field line should be vertical. Here, E2 would be 0. If you know the electric field just out of the conductor, which is E1, and using that information, you can obtain the charge distribution at that point. Well, let's continue with the second surface. Well, in the second surface, it's basically the identical derivation. E and ds are in the same direction at the top. They are in the opposite direction at the bottom. So E3 will have a minus sign. E2 minus E3. This should be equal to sigma 2 over epsilon 0. This is my second equation. Now we can do the same thing here. This time I have only E1 and E3. E1 minus E3. This is equal to sigma 1 plus sigma 2. This is the total charge distribution inside time divided by epsilon 0. So this is, at least we hope that this would be our third equation. But you see, if you just sum these two equations, you get this one. This is not an independent equation. We have three unknowns, but just two equations. This is an example where we cannot determine the electric field by just using Gauss law. We can apply the Gauss law. There is no problem in the application of the Gauss law, but we cannot determine the electric field without an additional input. I mean, we already using the symmetry properties, we are giving some input to our Gauss law. We are telling you, okay, the electric field has to be in this direction, in that direction. It can only depend on this and that. That is the first step you have to do. But at least in this example, it turns out that the input that we have found by just using symmetry arguments was not enough to determine the electric field. We still have to know one more thing. And that additional thing was, for example, when sigma 1 and sigma 2, they are equal in magnitude but opposite in direction. We said that, okay, E3 is 0. If E3 is 0, E3 is 0, and E3 is 0, this is 0, so E2 is sigma over epsilon 0. But minus E2 is, we said that if these are opposite in charge, so minus E2 will be just sigma 1 over epsilon 0, and hence E1 should also be 0. But this is an additional input. Without that additional input, we cannot determine the electric field. So Gauss law, I mean, don't take me wrong, Gauss law is always valid. Whatever your configuration is, whatever your surface is, Gauss law is always valid. Now the problem is, it is correct, but will you be able to make use of it to obtain the electric field? It's only in very special cases where, I mean, you can just drive the electric field using Gauss law. And even in those cases, we have to give some input to the system. Like the symmetries, we have to say that, okay, this is the direction of the electric field. It can only depend on this and that. With this information, plus the Gauss law, we can determine the electric field, if we are lucky. Well, let's give a break, a 10-minute break, and after the break, we will continue.